Okay, so what we're going to do today is we're going to go into lab number 2. Or excuse me, not lab number 2, but lab number 1. And in lab number 1, what we're going to do is we are going to examine, if you look on the camera here, I don't have an overhead, but I got this. Introduction to motion. The purpose of lab number 1 is to discover how to use a motion detector, to explore how various motions are represented on a distance or position versus time graph, to explore how various motions are represented on a velocity time graph, to discover the relationship between position time and velocity time graphs, and to begin to explore acceleration versus time graphs. Now, in this lab, we're going to look at motion. Motion is simply how position changes over time. But there are various properties that we're going to deal with. We're going to use a motion detector to plot position versus time and velocity versus time graph in the motion of your own body and a cart. The study of motion and its mathematical and graphical representation is known as kinematics. Now, I do realize that I am literally reading out of the book, but that's because I want you to get in the habit of actually doing all the steps. If you recall, when we did the making sense activity last week, it's make a hypothesis, make a predicted outcome, do an experiment, compare that to the predicted outcome. So I want to do that same kind of pace for these labs here. So we're going to start off investigation number 1. The way the labs are set up is, of course, we've got 12 labs. Each of those labs are broken into investigations. Each of those investigations has a goal, and they have a series of activities which will lead us towards that goal. So in investigation 1, we're going to start off with position time graphs. The material is already set up. Yeah, I got it set up properly. Comment. Distance is short for distance from the motion detector. The motion detector is the origin from which distances are measured. The motion detector detects the closest object directly in front of it, including your arms if you swing them as you walk, transfers information to the computer via the interface so that you walk or jump or run. The graph on the computer screen displays your distance from the motion detector, and it will not correctly measure anything closer than some distance. So in this case, if it's within about 30 centimeters, the motion sensor doesn't see it. If it's beyond 4 meters, the motion sensor won't see it. So far, so good, right? Now, to make life a little bit easier, this is my 0 mark. This tape right here is 0. This tape right here is about 2 meters away from the motion sensor. And this tape right here is about 4 meters from the motion sensor. So that shows you the range of motion that we're going to be working with. Okay, so what are we going to do? Let's go ahead and start the activities. First, we're going to go ahead and do some motion here. Step number 3 in activity 1-1, begin graphing and make distance time graphs for the different walking speeds and directions. So A is walking away from the motion sensor at a slow, steady pace. B is walking away from this motion sensor at a faster pace. C is walking towards the motion sensor at a slow, steady pace. And D is walking towards the motion sensor at a faster pace. All right? Pretty easy, yes? Question? Go get it. I double time it too because you're going to miss stuff as we go. Anybody else forget their equipment? Their notebooks, stuff like that? Okay. So, we're going to start off with a volunteer. You volunteer. Come on down. What I want you to do is stand in front of the motion sensor. Right about here is fine, okay? And let me change the camera aspect so we can actually see you move. Again, thank you for your patience, everybody, because I'm going to be doing this a lot. Okay? So all I need you to do is to move away from the motion sensor at a slow, steady pace. When you hear the clicking, go ahead and start moving. Okay, hold on a moment. I think I got an error here. I know what the problem is. Let's see. Let's try now. Oh, there we go. Okay, hold on. All right, now that I think I got the technical issues cleared, when you hear the clicking, go ahead and get started. Okay, that works just fine. Go ahead and have a seat, thank you. It's a little slower than I expected, but that's quite all right. Okay, now go ahead and jot that down on. Go ahead and jot that down in the text in your lab book, down on the section down here. Next question, next person. You've got to tell me how to say your first name. Is it Pution or Pution? Tian. Okay, come on down. Come on down. Okay, start right there. This time I want you to move away at a faster pace. Okay, yeah? All right, so when you hear the clicking, go ahead and go. All right, that works fine. Oops, there we go. All right, that works fine, thank you. All right, not too bad. All right, now, because I can't see your name tag, I still don't know who you are. Well, come on down. This time I want you to move towards, so where that second tape mark is right there, I want you to come towards the motion sensor at a slow, steady pace. All right, that works just fine, thank you. And now, come on down. Same starting position, I want you to move toward the motion sensor at a faster pace. All right, that's all I need, thank you very much. Now you look at that and you go, how am I going to compare them? So let me show you the runs again. This is, well, that's the one I don't need, so let's delete that. Uh-oh, I think I deleted. Okay, hold on. Let's see, did I get it back? Yes, no, I did not, so Control Z. There we go, got it back, good. The nice thing is, if you make a mistake with this computer program, all you need to do is hit Control Z. It has an infinite amount of undos. All right, so here's the first run moving away at a slow, steady pace. Here's the second, here's moving away at a somewhat faster pace. Here is moving toward at a slow, steady pace. Here is moving toward at a faster pace. So now we get to answer the questions. Question 1-1. Right? Question 1-1. Describe the difference between a graph made by walking away slowly and one made by walking away quickly. Yes? The slope of the line is steeper under what condition? Okay. Here's the way we can prove it. I can put both these runs on the same graph. So the blue run is walking away slowly. The red run is walking away quicker. So in this case, we can see, yes, that is the case. If you're walking away, how fast you are is the steepness of the slope. How about question 1-2? Describe the difference between a graph made by walking towards versus one made by walking away. What's the difference? Yes? Okay, well, this is a comparison between walking away versus walking towards. So what would be the difference? Excuse me? Walking towards would have a negative slope, so let me go ahead and show that one. And now you see, the green one is walking towards, and the red one is walking away. So as you can see, walking towards would have a slope that it's sloping downward, whereas walking away would have a slope that's going upward. Okay? Everything good so far, right? Okay, that leads us to the comment. It is common to refer to the distance of an object from some origin as the position of the object. So now we're going to refer to our graphs, instead of being distance time graphs, we're going to refer to these as position versus time graphs. Okay, so prediction 1-1. Predict the position time graph produced when a person starts at the 1 meter mark, walks away from the detector slowly and steadily for 5 seconds, stops for 5 seconds, then walks towards the detector twice as fast. Compare the predictions with others and your neighbors, and then draw your prediction on the left-hand axis below the solid line. So here, on the left-hand side, go ahead and draw your prediction. Going to walk away at a steady pace for 5 seconds, stop for 5 seconds, then walk towards the motion sensor, but at about twice the speed. What would your graph look like? Okay, so that's where we're going to make the prediction. Now, of course, when we make a prediction, we now have to do the test. By the way, what does it kind of look like? Can you give me a description? Anybody over here? I'll go over here. Anybody over here? Give me a description. What it's going to look like. Okay, so it's going to be sloping upward for 5 seconds. And then what's it going to do? Stay flat. Okay, and then what's it going to do? Okay, is it going to be the same? Is it going to be the same steepness? No, shouldn't be the same steepness. So comes the test. Mr. St. Nicholas, you get to volunteer. You get to do, we're going to start to get a little bit more complicated here now, right? Yes. Okay, so again, you're going to start at about 1 meter away. So this is about 1 meter away, right about here. Okay, so you're going to start about here. Then you're going to move back for 5 seconds. You're going to stop for 5 seconds, and then you're going to move forward back to here at about twice the speed, okay? Now, as you can see, we have a time scale that'll allow you to kind of mark your time. We also have a clock down here as well, okay? Don't worry if you don't get it right the first time. That's why we do, that's the nice thing about computer. We can redo the experiment. Let me go ahead and, so that everybody can see the actual motion. Okay. All right, so. Okay, now okay, we're going to stop here because now we got a technical error. Not a problem, it's just that the time scale didn't change, right? So that's easy enough. First of all, I'll turn that off. And then I'll change the time scale. Now it makes a little bit more sense, doesn't it? So go back to the starting position, and we're going to try it again. Go ahead. And stop. And go. Okay, excellent. Now taking a look at this graph, go ahead and sketch that graph on the final result on the left-hand side of the page, on page 5. And that way we go to the next question, which is, does it match your prediction? All right? So when I go to question 1-3, is your prediction the same as the final results? If not, describe how you would move to make the graph that looks like your prediction. All good, right? All right, excellent, fantastic. Now we're going to do something even more interesting. In activity 1-2, by now you should have a pretty good idea of predicting the shape of a position time graph depending upon your motion. Can you do things the other way around? That is to say, I give you the graph, can you move to the position time graph? See, before it's you move and here's the graph. Now it's here's the graph, you move to match it. So here's what I'm going to do. I'm going to turn on a prediction. As you can see, the prediction lasts for about 18 seconds. Okay, And I'm going to move this over a little bit so we can see it a little better. Okay. Got it all set there? Okay. Now comes the fun part. I'm going to skip a little. Mr. Gaines, come on down. I'm going to give you the fun one. What I want you to do is I want you to move so that your motion lies on top of that graph. Okay? Now, where are you going to start? Right about there, about half meter mark, okay? What are you going to do for the first few seconds? Stand there for how long? 6 seconds, okay. Then what are you going to do? Okay, if you're walking which way? If you're walking back toward the back of the room, what should the slope of the graph look like then? It would go down? Well, but here's the thing. Wouldn't you say that you're getting farther away from the motion sensor? That is to say, where you're at right now is half a meter, but if you move backwards, you'd be a meter away, and if you keep moving backwards, you'd be like 2 meters away and so on down. So doesn't your position increase then? So if your position increases, then the slope should go up, shouldn't it? So how would you move when you do get started? Well, not the speed, but which direction? Back that way, that's correct. Until when? And then what do you do? Okay? And then what are you going to do? Okay, in which direction? Back toward the back of the room. That's right. Away from the motion detector. Okay, well then, now that you told me what you're going to do, let's go ahead and do it. Okay, hold on a moment. We got to do something here. All right, ready? I don't think that worked. That's okay. Come on back. We're going to try it again. No, you're going to do this because you're going to learn as you go. Okay. So this time, what we're going to do, well, it's real simple. Okay. So what do you think the first mistake was? You weren't close enough. Okay. Here's how we're going to check. I'm just going to go ahead and start recording just to see where you are. That's not too bad. Okay. So let me go ahead and get rid of those last 2 runs. And now, let's go ahead and try it. Faster. Oh, okay, not quite. All right, so let's see if we can work on that part again. Okay, as you can see, you got to go faster, don't you? Okay, so let's go ahead and try it again. Don't worry about the position. Just start moving when you're supposed to. Okay, wait a minute. Now comes the hard part. Slower. I told you. Okay, we're going to do one more time here. You got the right idea, except now that last part, you really got to slow down, don't you? You notice that? Okay, we're going to do one more time. All right, no pressure. That's okay. I'm going to pull somebody else out. Okay, why don't you go ahead and step back a little bit. All right. There we go. Okay, that's better, but okay, now you got about the right idea about the speed coming back, although it's a little too slow. How do I know it's too slow? Because the slope is too shallow compared to one more time. One more time. You can do it. Don't worry about the position. Okay, good. All right. Good job. Good job. It feels weird, doesn't it? Because when you first move, you establish a speed, but then you got to move. How do you have to move at the end of it? Much slower, don't you? And it's really hard to do that. Okay? I'm going to choose you. Come on down, Mr. Besk. I almost wanted to say, I choose, Pokemon, I choose. Sorry. I told you I'm going off on tangents. We're going to do one more time, aren't we? Okay. And by the way, if he ends up doesn't match, that's okay. As I said before, it's going to be a lot of muscle memory. So let's go ahead and give this a go. Don't worry about the position. We can fix that on the next run. And there will be another run. And now you see why there's going to be another run. Go ahead. Okay, come on back. It's not that easy, is it? No, that's all right. But the thing is, okay, well, let's go ahead and try it one more time. Yeah. There we go. Okay. Yes, sir. Yeah. Oh, there we go. Good adjustment. Yes, sir. Yeah. Very good adjustment. All right, good job. Good job. Okay. Now let's go ahead and answer the questions here. Question 1-4, which is, what is the difference in the way you move to produce the two different sloped parts of the graph? Okay. How did you have to move to do this part of the graph compared to this part of the graph? Okay. What say you? How did you have to move? You're the one who moved it, so how did you have to move to be the difference between the 6 to 8 seconds compared to the 12 to 16 seconds? Much slower, yes. Okay, excellent. Okay. Now, what I would like you to do is, let's go ahead and do some other position time graphs. So I'm going to give you a couple minutes. Make up your own kind of graph. Make up your own graph. Okay? And then, after you make up the graph, I'll get about 2 or 3 of you to come in and see if you can match the graph that you made up. Okay? So make up your own type of graph. Sketch it in on page 7 on the axes there. And then we'll see how that kind of works out. So I'm starting to record the movie. So we're going to start with that particular prediction. Let's see if we can match this. A positive slope, standstill, and a steeper negative slope, excuse me. Okay, that's 4 seconds. Here we are at 8. Oh, it's tougher to do, isn't it? Because here's 16 all the way over here. Okay. Let's give it another go, because I actually do like this. I do like that graph. So let's go ahead and try it again. Okay. There's 8. Remember, you're going all the way over here. All right, that works. That works. Very good. Okay, not bad at all. Did he match for the most part? Okay. Now, Mr. Markham, let's go ahead and give it a go. I'm kind of curious to see what you came up with. Oh. This is going to be fun. Where are you going to start at? Okay. So the good news is there's that mark right there, this paper right here, that's 4 meters. Here's 2 meters. So you pick the marks that actually works, okay? Now, how fast are you going to move back to the 4 meter mark compared to moving towards? About the same speed, okay. And then you got to come into 0 and don't kill yourself in the process. So let's go ahead and give it a go. There's the 2, not bad at all. There's 8 seconds. Okay, good. And now you got to come right back. Yeah, okay. Not bad. Here's the top of it. Okay. Now, that's because you stopped for a while. Do you want to give it another go?
I understood what I did wrong.
Okay, not a problem. Okay. All right. Not bad. We're going to move on now. We're going to move on. What we're going to do now is we're going to take a look at these graphs here. Question on step number 3. Can you make the curved position time graphs? See those three, A, B, and C? Okay. So step number 4 says, describe how you must move to produce the position time graphs. So how would you move to make graph A? How would you move to make graph B? How would you move to make graph C? Write it down. Okay? The writing it down is part of the prediction process. Okay? And of course, since that's the prediction process, what comes afterwards? The experiment. Exactly right. Okay. All right, now I'm going to do this. Since I don't have a mechanical zoom, or rather an optical zoom, okay, there we go. All right. All right, I'm gonna throw a dart, and my dart lands on Mr. Gonzalez. Come on down. So, quick question. How would you move to match this graph A?
To match that graph, I would move backwards at an increasing speed and then go very fast again.
Okay, so where are you going to start at? Come on down then. Let's see how the graph looks. Okay, so I'm going to start, when you hear the clicking, go ahead and start moving. No, okay, hold on, my fault. This time scale is really, really big. We really only need about 4 or 5 seconds. So let's give it another go. Okay. That's a bit of a jump. Can you do, here's the thing, take a look at this line. How does that look? Does it have any jerk or any corners to it? So how do you want to move then? How do you want to transition? Well, you want to transition smoothly. Okay, so let's give it a try again. Okay. Okay, don't hold back. There we go. That's what we're looking for. Okay, so as you can see here, the slope has changed, hasn't it? Okay, well, go ahead and have a seat. Next door neighbor. Yeah, in our raincoat here. You get one a little more interesting. You get graph B. Now, how would you move to match that?
Start close.
Yeah?
And I start off fast.
Okay.
And I slow down.
So should you start from a standing position, or should you be moving? Okay. Okay. Sounds like a plan. So when you hear the clicking, you can go ahead and start. Okay. All right, not too bad, not too bad. We start off steep and we kind of flatten out there. Okay, not bad at all. All right, back corner over there. You were looking at me. It's like, I want to do this. Okay. You get that one. Graph number C, where are you going to start? Okay, that second tape line is the 4-meter mark, so come on up to that. That tape line right by your foot, that's a 4-meter mark. It can't see beyond that, that's why I say. Okay, and then what are you going to do as you come toward it? Okay, let's go ahead and do it then. Okay, let's give it another go because it's, while you've got the right idea, it's kind of hard to see it. Okay, the problem is the time scale again. All right, so let's go ahead and give it another go. There we go. Oop. Okay, don't mind all this stuff. But as you can see, we started out relatively flat, and then it sped up like that. So that leads us to our questions. That leads us to our question 1-5, which is, whoops, not there. Our question 1-5, what is the general difference between motion that results in a straight line graph and on a position versus time graph, and that results in a curved graph on the position versus time graph? What is the difference? Yes? Constant speed versus changing speed. That's the thing. If the speed is constant, the line looks straight. But if the speed changes, then the line is going to change. If you speed up, what happens to the steepness? It gets more. That's correct. Whether it's sloping more downward or more upward. If you slow down, what happens to the steepness? As you slow down, what happens to the steepness of the line? It flattens out, doesn't it? Okay. Okay, excellent. All right, let's take about 5-6 minutes. A number of you may need to go over to the head and get a drink or something like that, and then we'll pick back up with investigation 2.